and then it's over to you.
Okay. Well, it's going to be a very simple talk with few maybe technical slides, but I'm not going to go into too many technical details.
Oh, that's fantastic. Yeah, no, we had around, I don't remember, last time I checked, there were around 50 participants. And the rule of thumb is that between half and 2/3 then are actually there. And some people decide to watch it then offline later. Yeah. Okay, let's wait maybe one more minute, because now we are at 30. And
Sure.
and then I quickly introduce you. Okay, we waited 2 minutes. I think we can start now. Okay, so good afternoon, everybody. Welcome to this edition of the NITheP Colloquium. My name is Francesco Petruccione. I'm the interim director of NITheP at the moment. And it is my pleasure this afternoon to introduce Professor Artur Ekert, today's speakers. Artur is a professor of quantum physics at the Mathematical Institute of the University of Oxford, and he's also Lee Kong Chan Centennial Professor at the National University of Singapore, and was, I think, until very recently, also director of the Center of Quantum Technology in Singapore. Artur contributed some seminal papers to quantum cryptography and quantum computing. In particular, he's probably famous for many things, but I think one of his papers in 1991 was probably one of the breakthrough papers in which that kickstarted the second quantum revolution, where he's demonstrated that with crazy things like entanglement, you can actually solve really important problems. Artur won many prizes, and I won't list them because otherwise there won't be time to listen to his talk. But most recently, he was awarded the very prestigious Michus Quantum Prize. I think it was last. Yeah. Artur, people are not here to listen to me, but they are here to listen to you. And if you Google Artur, you will find many more interesting things about his life and his achievements. Artur, we are really very happy that you're here with us today, and we are really keen to listen to your talk. Before I ask you to start, just a reminder to the participants to please make use of the question and answer facility at the bottom of your screen. And Ilya Sinaisky, that you also see on the panel at the top of your screen, will coordinate the question and answer session after Artur's presentation. So Artur, thank you very much for being with us this afternoon, or this evening for you, since you are in Singapore. And please, you can start your presentation. Thank you very much.
Well, thank you, Francesco, and thank you very much for this invitation. And thank you, Ilya, for taking care of the technical side of this. And good afternoon to all of you in Africa. And as Francesco said, I'm in Singapore at the moment, and it's evening here, but it's great fun to use this facility, and in those weird times to be able to give a talk remotely. So today I'm going to tell you, it's going to be not a very technical talk. I would like to tell you a story that started in 1991, maybe perhaps even in 1990, and it has this sort of interesting conclusion in last year. So it is a story about this entanglement-based quantum cryptography and experimental demonstration on a rather grand scale. But I would like to show you how in those 30 years that more or less separated the two events, lots of interesting physics and lots of interesting ideas appeared. So it's kind of like a talk about where underlying question is the ultimate limit of privacy. Can we really communicate with absolute security, and what kind of conditions have to be satisfied for this to be possible? Now, I have to also apologize. It may happen, this technology, it's kind of embarrassing to admit that I haven't been using Zoom that often during the COVID time. So every now and then I may press something completely stupid. So then I just only hope that Ilya will just correct my errors. Anyway, so, when one talks about secure communication, of course, there are many possible approaches, and one is a historical approach to the subject. One can give a talk about how it all started, how people, soon after inventing writing, started writing secret messages, and the whole history of secure communication goes back to about 400 BC to ancient Greeks in Europe. But this is not this kind of talk. So just so I'm going to skip this historical introduction. And so this is just the only slide I have to let you know that there's to those of you who are interested, there's a wonderful story that of how the code makers and code breakers try to outsmart each other. So whenever people came up with some brilliant ideas to encode messages or encrypt messages, sooner or later someone else came up with the ways of breaking them. So you may ask this question, is there such a thing like a perfect cipher? And this kind of questions will take us into modern, basically into 1940s, and the work of a few people, in particular Claude Shannon, who, as you probably know, was the founding father of a modern information theory. But he also, before he wrote his seminal paper on how to communicate information, how to encode information, he was very much interested in how secure information can be. So he was the one who proved that the following system, if you use it well, is considered to be absolutely perfect. So this system is known as a one-time part, and it works roughly like this. So we have two individuals here, as you can see on my slide. One on the left is, we call her Alice, and the person on the right, we call him Bob. Alice and Bob want to communicate in a secure way, and they would like to do it in such a way that any third party, what usually called an eavesdropper, Eve, is actually excluded from this, cannot eavesdrop the communication. So one way of doing this is to take a message which you can just write in any language using any alphabet. In this case, you can see this message at the top. So let me actually try to see whether I can use pen. It's going to be experiment. Let me see whether I can just use this. So I don't see it working. Well, never mind. So just anyway. So here's the message that you can see. The message is written in binary. Alice has a message, and she wants to send this message to Bob. And she wants to send this message in such a way that he gets exactly the same sequence of 0 and 1s, but nobody can actually guess what this message is, and whoever tries to intercept this message will have no idea what it is. So how to secure this message? So one way to do is to encrypt it. And the way this encryption works is explained in this simple diagram here. So you take you assume, you can see that there is a, right below the message on the Alice side, there is something called the cryptographic key, the string, binary string of 0s and 1s, which is completely random. It doesn't have any pattern to it. And the encryption method works by binary addition. So you take a message and you take the key, write the message, write the key below, and you do bit by bit addition. So you take, going from the left to the right, you just add 0 to 0, and then you get the first bit of your cryptogram, which is 0. Then you have 1 plus 1 in binary, that's 0. So you have another bit of the cryptogram, and then you have 1 plus 0, which is 1, and so on and so forth. So you basically superimpose your message on this cryptographic key, and then you obtain the cryptogram. The cryptogram is as random as the key, essentially. And you send the cryptogram to Bob, who then, it is assumed that Bob has the same key, and Bob takes the cryptogram and performs the same operation, and he superimposes the cryptogram to the key. So it's by doing the binary addition, and recovers the message. Now, Claude Shannon managed to show that this system is perfect in a sense that it cannot be broken, because the cryptogram has 0 statistical pattern. So it doesn't have any statistical pattern that you can use as a cryptanalyst to break the cipher. But this comes with assumption. The assumption is that the key is truly random. It's secret. It's known only to Alice and Bob, as long as the message, and it's never reused. So this one-time pad is a very demanding kind of encryption method, because every single time you have a new message, you have to have the key. And the key somehow, has to be owned by Alice and Bob, and it has to be secure. So that's all very well. We have a perfect cipher, but that begs the question, of course, how Alice and Bob can then establish this huge supply of cryptographic keys for subsequent encryption. Quite often people ask, why do we need a cryptographic key? Why do we sort of separate the encryption into 2 parts, the key distribution and then sending cryptograms? Well, the key distribution is just a simple process, well, kind of conceptually simple process, where we would like Alice and Bob to end up with a completely random and meaningless strings of zeros and ones, as long as they satisfy the condition, namely that it's truly random, it's secret, and it's perfectly correlated. So Alice and Bob have the same sequence of zeros and ones. So now the reason we want to do it is that we really don't know when we want to send meaningful encrypted messages. The key can be distributed anytime. It's just because it's not the message, doesn't carry any information. It is used as a substrate later on when there is a need to send a message, when the moment comes, and Alice at this very moment wants to send a message to Bob. She grabs the key and is using this key to send the message. So it's just sort of molding the key into the message. So therefore, it's very convenient to separate the key distribution from sending messages. Now, the second comment here is that the key distribution is a big problem, because it has to be done over a very secure channel. Alice and Bob perhaps can meet together. But once this key is established, the encryption can go over any unprotected public channel, simply because it is the key that protects the message. So all fine, except that we have this key distribution problem. How come Alice and Bob, being miles away from each other, can distribute the key with perfect security? And that was a problem that cryptographers tried to solve. It was like a holy grail of secure communication, find the solution to the key distribution problem. So today we essentially have two ways of dealing with the key distribution. So if you take one-time pad, I'm not necessarily saying that one-time pad is the most practical thing to use. It's just, but let's take it as an example, because indeed it is the only system that has been proven to have information security that is a perfect cipher. So if you take this one-time plot and you notice the key distribution problem, then you ask how you're going to solve it. Then there are two ways to do it, essentially. One is a beautiful mathematical approach where you see on the left of this slide. It's called public key systems, where, and I'm not going to go into details to describe how it works, but it's a beautiful piece of mathematics which essentially just deals with not with one key but two keys. One is publicly known, the other one is private, and using this simple mathematics, one can actually design a system where Alice and Bob can communicate without really a need for key distribution. Now, the thing is that, by the way, those are the very common ciphers that we use today when we communicate on internet, when you want to secure your banking transactions and the like. The problem with those, with this solution, is beautiful, and it's very practical and works very nicely, but it's not quite proven to be secure, in a sense that the public key crypto systems rely on the fact that certain mathematical problems have some embedded difficulties, and for example, that if you want to factor large integers, it might be difficult in a sense that it takes computers lots of time, and you rely on this when you design the ciphers. There is a danger that some of the public key crypto systems will be compromised once we have a quantum computer, for example. So quantum technology is a serious issue for public key crypto system to the extent that quite recently National Security Agency, which is an agency in the United States that takes care of secure communication, for government secure communication, and in a way is instrumental in setting up standards for secure communication, issued a challenge, an open challenge, to find a public key crypto system that will be resistant to quantum attacks when we have a quantum computer. So that is something that I'm not going to talk about. Yet another interesting topic for a talk. I'm going to tell you a little bit about another solution that came from physics, and it's known as quantum cryptography. Now, there are essentially two approaches to quantum cryptography. Again, one is called prepare and measure, that was proposed by my colleagues Charlie Bennett and Gilles Brassard. And it has some issues. I mean, the main issue is that you have to be very careful for the so-called side channels. You never know, once you prepare something and send to someone else, whether your quantum signal may be correlated with some other degrees of freedom that you cannot control. So that is a big issue in general with prepare and measure system. The other one is based on entanglement, and that is what I'm going to talk about. Not necessarily because I was behind designing the system, but because I think this idea led into interesting further developments, namely device-independent cryptography, which I would like to tell you about, and which I think is where we are pushing the whole notion of security to limits. So historically, as I said, the quantum cryptography was, if you look at it from chronological perspective, was proposed by Stephen Wiesner, but Stephen didn't quite publish his manuscript and was neglected, except that luckily Charlie Bennett knew about Wiesner's work, and Wiesner was interested in using quantum phenomena like Heisenberg uncertainty principle for designing banknotes that you cannot forge. Charlie and Gilles translated this into key distribution, and that's how prepare and measure surface roughly in 1984. My approach to quantum crypto was completely independent. I was not aware of that work. It was public. First of all, it was before internet, and it was published as a conference proceeding in some obscure publication in India, so in Bangalore, and I had basically that was not available. So my approach was different. I was based on Bell inequalities, and only later I learned about their work. Well, needless to say, at the time I was a student, so I was a bit disappointed that someone else had this idea before, but at the same time I was in a way happy because it was good to feel that I was touching up an idea that some big guys were working on, so that means that it probably makes sense. So therefore the story that I'm going to tell you is a story how two things I would like to connect this time back in Oxford when I was working on this. It was in 1991, and I was a PhD student at the time, trying to think about some other quantum optical problems, like improving channel capacity for optical communication, but sort of deviated into quantum crypto. It was a purely theoretical work, and I never, honestly, if you ask me back in 1991, I would never say that in my lifetime anyone will actually be doing that kind of stuff, because it was truly blue sky and a project of a product of my imagination more than anything else. But here we are, last year in China there was a beautiful demonstration of exactly the scheme, more or less the scheme that I proposed, on the scale that is stunning, because the Chinese managed to put a satellite, a dedicated satellite, on the orbit. It's about 500 kilometers or so above the surface of the Earth, and it's sending entangled photons into two places in China, which are separated by about 1,120 kilometers, and the system is just about. I'm saying just about because that the data rate and especially the finite key rate is still a question of interpretation. But nonetheless, one can certainly just say that this technology is capable of establishing a reasonable number of secure bits between two different locations in China. So that's fantastic thing, and I have to say, I felt when that this experiment in a way is a closure of a certain path that I personally covered from 1991 to 2019, and but on this path a few things happen, and I would like to explain this. By the way, I'm just not sure how much time do I have?
Arthur, ideally around an hour, but plus minus reasonable error margin.
Okay, I'll try not to stretch your patience too much, and so okay, so the story about connections between key distribution and Bell inequalities can be essentially traced to a paper, a seminal APR paper that Einstein and his colleagues Podolsky and Rosen wrote back in 1935. In this paper, Einstein, who was not so happy with the formulation of quantum theory, he thought that it just not only just makes this relies too much on the notion of randomness that he didn't think was inherent into the theory, and thought it was just a phenomenological construction that has to be changed. And Einstein was then coming up with all kind of things that were challenging the mathematical dogma of quantum theory. And one of them, in particular this paper, was challenging to the concept, even the concept of reality. Do things exist out there if you take quantum physics seriously? So, and in particular, Einstein defined something that he calls an element of reality as something that goes this: if without in any way disturbing a system, we can predict with certainty, that is with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. So when I read this paper, I have to say, to me, it sounded almost like a definition of perfect eavesdropper. So that's what, so you think, okay, all information is physical, and therefore there has to be, when you think about encoded information, there has to be an element of physical reality associated with a signal, in particular with the two values, 0 and 1, that are encoded there. And what an eavesdropper wants to do is to learn about this physical, the element of physical reality. It wants to learn the value of the physical quantity, whether it's 0 or 1, without disturbing it, so that Alice and Bob think that there was just a perfect transmission, and nonetheless Eve has this value. So that sort of prompted me, this one sentence, the definition of the element of reality, pushed me to think, knowing of course that what happened later, where John Bell and others, pushed me to think, well, maybe then we can use the concept of EPR and then later the Bell inequalities as a test for eavesdropping. So that sort of, so let me just elaborate a little bit so that you just get the concept before we'll go into details. So think about polarization, for example. It's an interesting property of a photon, and we cannot just measure a polarization, but we measure polarization with respect to some specified direction. And in any single measurement, we can get two outcomes, two results, call it +1 or -1 in the units of h bar, but you can also interpret +1, for example, as 1 and -1 as binary 0. So this is just a question of convention. But let's stick to +1 or -1 for the derivation of Bell inequalities. So you may say, okay, well, a question whether a polarization is there when you have a device. A device would have a knob which you sort of set up to measure a polarization with respect to a certain direction in space, and then a photon goes into this device, as you can see, and there are two outcomes that are possible, either +1 or -1. So you may say, well, asking whether there is a polarization prior to photon entering this device is a bit weird, because you say, well, of course there must be. So the measurement, the classical way of thinking is that the measurement essentially tells you about the pre-existing conditions. It's just if something is red and you measure the color, then you get the answer, this object is red. So you may think that, in the quantum world, it is pretty much the same, that the measurement is uncovering pre-existing conditions. But of course, so the question is, do photons always have predetermined values of polarizations prior to measurements? Well, of course, the answer, as you know, or those of you who are interested in quantum or into quantum know that is not the case. At least not in a very simplistic sense as it is in the classical world. And John Bell was the one who took Einstein worries and turned them into a testable proposition. He said, well, it's not a philosophical question. Actually, I can come up with a proposal for an experiment where you can see that there may be an issue with the pre-existing values. And that's known today as Bell inequalities. I think I personally consider this as a very deep and profound statement. And the beauty of this Bell inequalities, at least in the way well, first of all, there are many ways of writing Bell inequalities, but the one I'm just trying to show on this transparency here and explain is known as a CHSH inequality. It's just like a different version of Bell's inequality. And so here's a one-slide derivation of this Bell inequality, and it's certainly worth doing this because, as I say, it is a profound statement about nature. So you can imagine that Alice and Bob receive photons from a source that is somewhere outside. And for each incoming photon, Alice is going to choose between two different orientation in space along which she's going to measure this photon. Call it polarization A1 or polarization A2. A1 and A2, each of them can have two different values, +1 or -1. And the same for Bob. He's going to choose another direction. For each incoming photon, he's going to choose the direction and measure the polarization. So he will be measuring either B1 or B2. And again, B1 and B2 have two values, either +1 or -1. So then, and then you repeat this measurement. So imagine that there's a source, it generates those photons and they come into those devices to Alice. One goes to Alice, another one goes to Bob. And a number of you repeat this many times. So then if you think about A1, A2, B1 and B2 as a binary random variable, then you can consider also S the new random variable, that is a function of A1, A2, B1 and B2, which is written here. And you can see that this S can be only +2 or -2. And it's kind of obvious because you say, if it is the case that the B1, B2, A1, and A2 do really exist, they have numerical values before they just come into those devices that measure them. And we do assume that in this case, for example, that even if Alice is choosing to measure A1 and learn the value of A1, we assume that there also is probably a value of A2, which we don't measure, but it might be there. So assuming that those values do exist, then you have this figure of merit S, and you can see that B1 and B2 can be either the same or could be different. Therefore, those two terms in the brackets are either 0 or ±2, and therefore the whole S can only take two values, +2 and -2. And so then if you take the average value, if you repeat this measurement many times and try to estimate S, so clearly sometimes it'll be +2, sometimes it's going to be -2, then the average value will be somewhere between -2 and 2. So that's it. So that's the Bell's inequality. There are tacit assumptions here, but basically the one that we use here says that the values do have existence. So B1 and B2, A1 and A2 do exist. And there are also some other assumptions about the fact that those devices do not know instantaneous communication, and those devices are responding to photons that are received from somewhere. They don't know anything in advance, and so on and so forth. So the reasonable assumptions. So so that's such a trivial mathematical statement that probably many people look at it and it went unnoticed for a while. And what John Bell did, he said, well, you know, if you look at this expression and write this figure, write the formula for the average value of S in terms of those polarizations, correlations between the polarizations. So So if you look at the average value of A1B1 or A1B2 or A2B1 and so on and so forth, and then if you then follow the quantum anomalies and then you see that it is known that if orientations A and B are theta degrees apart, then the results agree with probability sine squared theta over 2, and then you can calculate all those correlation coefficients here, and you notice that S actually can be larger than 2. So it's, instead of being in the range between -2 to 2, S in fact can be somewhere from -2 times square root of 2 to +2 times square root of 2. So it is quite a range, and that exceeds the interval from -2 to 2. And that's very surprising. So if you can violate those Bell inequalities, the question is, what does it mean? In fact, today we classify correlations into something that we call classical correlations. That and this here is a simple diagram. It has actually, it's not just a sequence of shapes to show the which subset is a subset of what, but it's just these polytopes that you can see have, it has some mathematical justification, but roughly we have classical correlations and a set of quantum correlations. So the classical correlations satisfy the Bell inequality. The absolute value of the average of S is less than 2 always. At most 2. The quantum correlations can push this value to 2 square root of 2. And then it turns out that there are also a broader class of correlation called non-signaling correlations, where this value can even be higher, but we are not going to talk about it. Those correlations were not observed in nature. It's a good question why. They have this property that they will not allow you to have instantaneous communication between two different parties. So they would respect the fact that the signal has to propagate from one place to another with some speed. And so all we see is this spherical shape of quantum correlations, but there could be a clear separation between classical and quantum. So we can see that there's a region here outside classical, so that means that S above 2 takes us somewhere into the quantum regime. And the question is, what does it mean? And what does it mean in particular for secure communication? Well, first, before getting too excited about it, Bell made a statement, but it took people a while to demonstrate that Bell inequalities are indeed violated. Perhaps most physicists at the time didn't think about this as something the most perhaps important experiment to do. It's difficult for me to know why. And then a few people tried. About a few years later, the most convincing experiments actually came 20 years later after Bell, where Alain Aspect did a fantastic experiment in Orsay. Alain was not the first to do this kind of experiments, but perhaps his one was the one that the community noticed and considered as a state of the art at the time. But today there are many experiments followed, and today we have ample of experimental evidence that the Bell inequalities are violated. So nobody doubts it. It's just a question of people now try to understand what does it really mean, and there's a question of all kind of different interpretation of this fact. But let's for the key distribution, what it means, and that was sort of like my way of thinking about it, is that if we can demonstrate that photons do not carry predetermined values of polarization, so somehow if those values didn't exist prior to measurements, so they were not then available to anybody, including eavesdroppers, right? There was nothing to measure. Once you measure, you make them somehow happen, and then then they do exist. They have this element of reality. But if Alice and Bob are the first to measure them, right, and then see the violation of the Bell inequalities, they do know that nobody touched those photos before. And that could be used as a test for eavesdropping. So that was simple and naive thing, but to take it from this idea to something that you can quantify was not that trivial. There's lots of mathematics and all kind of techniques people in computer science and cryptology use. So for example, the way, of course, you would distribute the key would be Alice and Bob would tune into a source of preferably highly entangled photons. Then they would just test on some subset of data whether Bell inequalities are violated. For this, they have to have public communication. Then the remaining set that is not revealed in public may still contain errors. It's not going to be perfectly synchronized. So they have to do something like a data reconciliation or error correction in public via public communication. That's possible. There are protocols for that, perfectly well known to cryptologists and people working in information theory. And then, even then, especially if there was the violation of the Bell inequalities was not saturated at 2 square root of 2, then you still have to assume that part of that fag might be due to an eavesdropper trying to an eavesdrop on this, and then you have to do something that is called privacy amplification. So there will define techniques on that, and then I'm not going to go into technicalities here, just to say that you have to estimate a certain quantity, the mean conditional mean entropy, and this parameter that you measure, the degree of violation of Bell inequality, actually allows you to put a lower bound on a certain property that cryptographers are after, and that in any classical scenario, it's basically impossible to measure this, and therefore to start this privacy amplification that I'm talking about. So that's let's keep that, and the question is, so how much of how the degree of the violation of Bell inequalities, how much secret bit is going to give you. So in asymptotic limit, where you have many distributions of this or many data, you can show that the secret key rate, which is roughly the number of secret bits that you get to the total number of bits that you distribute, is given by this blue curve that you see in the formula. So on the horizontal axis, you have this parameter S, which goes here from 2 to 2 square root of 2, and the secret key rate, how much secrecy you can get out of the system, is on the vertical axis. There is a red line here, to which I will just come in a moment, because now comes a very interesting conceptual idea. So the beautiful thing that happened was that after my work, people were looking into this, and the interesting thing is now to question the assumptions. So all I told you is a sort of old story. It's about 30 years old or so. But what came later is actually fascinating, because people started questioning assumptions and say, what do you really assume? How much do you have to assume to make sure that this system is secure? So clearly, you have to assume that Alice and Bob's labs are secure, that there's no information leaking there. So obviously, otherwise an eavesdropper might be looking into it. And we have to assume that Alice and Bob control and trust devices in the lab, at least in this original sense. There's also more subtle tacit assumption. We have to assume that Alice and Bob, when they make those random choices, which particular polarization to measure, whether it's going to be A1 or A2 or B1 or B2, or you can perhaps have a few more, somehow that this is done in a truly random way. If that is predetermined, or if that can be guessed in any way, then there is a possible attack on the system that Eve can explore this attack. But the beautiful thing was, even in the early version, was that actually we assume that Eve can distribute those photons to Alice and Bob, that the source, Eve can actually be the source of the photons, because if they see the violation of the Bell inequality, then they can establish the key, but given the conditions, that given the finite key rate. But if they don't, so if Eve is trying to control the source too much, in a sense of sending photons which are of non-polarization, then obviously there will be this element of physical reality, and then the Alice and Bob will see it, and it will not establish the key. So the question is, can you just look at this assumption, in particular the second one, and see whether we can deal with a situation where Alice and Bob do not have to control and trust devices in the labs. And so the beauty is that, and again, it was probably, I wish I could see it myself when I was working on this protocol, but it just only came later. Some of my colleagues noticed that it is not necessary to assume the devices that you have to trust devices. It doesn't really matter. It just could be a black box that can be even produced by Eve and given to you. And as long as those devices respond in a way that allow you to violate the Bell inequality, so namely you have a switch between, say, two different types of polarization. It may not even measure polarization. It may not, those devices may have some storage of entangled photons, whatever. As long as they respond, they allow you to do the two setting, and they respond with signals which you can interpret as +1 or -1. And then you can see the violation of Bell inequalities. Then you don't have to know anything about those devices, honestly. You don't have to know about the internal working. This data then can be translated into a secret key. And so that is known as a device independent scenario. So it is indeed the case that you can you can think about the situations where you do not have good technology to build quantum crypto devices, and then you go to someone whom you don't trust, and that person tells you, well, I can offer you can purchase it from me. You don't trust them at all, but nonetheless you can take devices of dubious provenance, you can take them, purchase them, and use them, because as soon as you see the violation of Bell inequality, it doesn't really matter. It doesn't really matter how things happen. That's the proof of the security works, and it's truly device independent. More often, you would like to have this system to protect you against your own engineering errors in the devices. So it may happen, for example, that quite often unintentionally we just implement something in a stupid way, or design things that are not so great, and that could be a security leak or a side channel. So this device independent thing tells you that hardware doesn't matter that much. As long as it satisfies certain criteria, you can run the test on those devices, and that external test tells you whether things are okay for security or not. So it is, you can even protect yourself against your own stupidity if you're not clever in building those devices. So that tells you, okay, once you see the violation, that's fine. Maybe you made some mistakes, but they're not crucial. So this device independent idea it's essentially the same protocol that I propose. It just simply has a different twist now. It shows that you can drop one assumption that was proposed by Tony Yassin, Nicola Bruno, Nicola Sang, and Stefano Piranha, Sertar, Valeria Scarani. So of course, you know, when you drop this assumption and you do the security analysis, then your key rate is not as good. So that it is certainly lower when you assume that you control your devices, that you have a device dependent scenario. But for a long period of time, by the way, that was a tough problem to estimate the key rate for truly device independent security, simply because you don't even have, there's the whole structure there is just of many security proofs was not so well defined. And it's only quite recently, in fact, that the class of most general attacks was reduced to some the so-called collective attacks that some other people came up earlier. So that today we know that actually device-independent key distribution is within the reach. It's not completely science fiction. It requires higher violation of Bell inequalities. It's pushing it towards almost like loophole-free violation of Bell inequalities, but it's certainly within the reach. So it's certainly easier to do device-independent quantum cryptography than to build a quantum computer in terms of the technology needed and the degree with which you have to control noise and so on and so forth. So the red curve just gives you the key rate for the device independence. So it's a beautiful idea. And so what is left in those assumptions? So the last thing that is left is that the assumption that those random choices for what to measure are really truly random. Even with device independent scenario, if you allow Alice and Bob to purchase the devices and also purchase random number generators that they may use to choose the values of A1, A2, or B1, B2, that's not good, because if those random number generators are prepared in a way that they are not truly really random, then we are in trouble. Sometimes people would say, you know, this is actually about Alice and Bob having free will to choose, but humans are usually terrible in making random choices. So let's think about random number generators. So that question is, can we fix that? Can we actually also get some lousy random number generators and improve them? So it turns out that yes, we can. There is the whole field, the beautiful field of randomness amplifications. We know that it can hardly be done in general case in a classical scenario, but we can, and I'm not going to go into details here, improve a little bit. We cannot do it completely from scratch. We have to just have a little bit of randomness. If we have epsilon of randomness, we can use quantum phenomena to amplify it. So at the end of the day, the situation today is like that with device-independent crypto plus ability to produce randomness amplification locally, we are having a mind-boggling situations where secure communication is possible with devices that you don't trust at all. It's just as long as you don't have to trust at all. I mean, sorry, the devices you trust, but not because of the mechanical procedure that you don't even control. That there could be black boxes. You trust them because you run the test and they certify themselves in the process of this Bell test. So that's sort of kind of remarkable. We can do that. Well, you know, so that sort of like completes the story that I wanted to tell you. It's been sort of long journey for the whole concept of quantum cryptography based on entanglement or Bell inequality, from something that was considered as a pure speculation to something that has been implemented, and in a big way, and probably the more will come, and it's still, there are many interesting open questions in the whole field, but some of them are tough mathematical questions, some of them are more conceptual, how you understand it, how does secure quantum key distribution lends itself to different interpretation of quantum theory, and so on and so forth. But that's, that's a topic on yet another more speculative seminar. So thank you very much for your attention.
Yeah, Artur, thank you so much for your nice presentation, and for bringing us through the history of your famous paper till the latest successes in testing it via satellite, which is really very, very impressive. Ilya, are there questions from our audience so far?
So far, no, but maybe, if the people raise their arm, we can give them permission to talk and they can ask their question directly.
Yes, we can do that. We are not so many. Yeah.
Yeah, there is Camille. Let me stop.
Yeah, please. Camille.
Hello, can you hear me?
Yes.
Yep. Yes.
Okay, so first, thank you for this nice talk and introduction. I just wanted to ask you if you can elaborate a bit more relating to the randomness. I mean, so one of the condition is that, or assumption is that Alice and Bob can choose randomly the basis of the measurement. And so my question is, for me, it's not really clear or obvious why this is so important. Like, meaning, if somebody can, so can you elaborate more on that? Why this is important, this third point?
Right. So imagine a situation that eavesdropper knows in advance which particular polarization will be measured by Alice and Bob, simply because an eavesdropper designed a random number generator, but it's a fake random number generator that looks like a random number generator, but it is pre-programmed. So the data are pre-programmed. So therefore, an eavesdropper knows for each particular instance for whenever those devices are about to register, then an eavesdropper really knows what basis will be used for, say, for the measurement of photons, if it is done in this way. So if that's the case, an eavesdropper can easily prepare those photons, because an eavesdropper also controls the source of photons, and send a well prepared data that will generate the outcome that eavesdropper can predict. It is essential that the choice of basis is not known to an eavesdropper, simply because otherwise everything would be predictable. It would be deterministic, and you can really just set up a very simple attack that would make the key known to eavesdropper as well.
Okay, yeah, I understand. So then comes my second question. So, I mean, the key point is that the eavesdropper cannot predict in which basis Bob and Alice are going to measure. So yeah, I guess from that came the of randomness. I mean, of choosing the measurement basis through random generator. But if you take just a simple assumption that this is like Bob, who is just at each measurement is choosing. So as you said, maybe we are not, as human beings, we are not very good generator of randomness. But even though it sounds quite difficult to imagine that a dropper can predict which base Bob is going to choose to make the measurement. So
Well,
wouldn't that be enough? Or I don't know, yeah.
yeah, so of course, you know, it's very interesting. It is a interesting problem. If people were tested about their perception of randomness, so it's very interesting to try the following experiment. Try to ask someone to write a sequence, say 100 binary digits, sequence of zeros and one that are random. And then, so let that person, you know, that person may just go and say, okay, well, 0, 0, 1, 0, 1, and will generate using only what he or she would consider as a truly random sequence. And then take a coin, or you know, a symmetric coin of some sort, and just toss it 100 times and register the data. And you know, most people will be able to tell the difference. Well, people who are, if you're into probability theory, you should be able to tell the difference. Which sequence was generated by a human being and which sequence was generated. So the human being who was trying to imitate a randomness, and which one was generated by a by genuine coin tossing. And you know, there are a few giveaways. So for example, one of them is that human beings tend to think that there should be more switches from 0 to 1. So that what we call a run. A run is how many times a given binary digit will repeat itself one after another in a sequence. So for example, a human being would say, you know, probably repeating 1 5 times is not such a good idea, and would probably try to avoid it. Well, usually that, you know, those runs actually are quite common, and if you do the truly random number generator. And there are many other, so you'll be surprised how easy it is to say, for example, that, this sequence was generated by a human being. Of course, you know, if you are a trained human being, someone who knows statistics, you may just counteract against it, and then you just try to make it look statistically plausible, and so on and so forth. So I can, you know, there's a long way to explain that a few other things, but of course, you know, the simplest answer, should just to go back to your question, is in real experiments, human beings would be just too slow. We want to have a quick data rate, so we have to have a random number generator integrated into the whole device that make those random decisions rather fast.
Okay, thank you. And maybe one last small question. So again, assuming that there is an eavesdropper which managed to guess some of the bases, but not all. I guess there's probably a threshold above which the eavesdropper managed to get the key, or to be able to later understand the message. Yeah, so I mean, are there some research or study related to this kind of threshold, or
yes, yes, of course. You know that there is a threshold at which, when you measure this parameter, the violation of CHSH inequality, there's a threshold below which you cannot extract any secret key. So even if of course, you know, eavesdropper may try some random guesses, but though security proof shows that that is not going to be helpful. Actually, this parameter S clearly defines the upper bound on amount of information that any eavesdropper can get out of the system.
Okay, thank you.
Okay, let's give Yadira a chance to ask her question.
Thank you, Prof. Ekert, for the very interesting talk. I have a non-technical question. What I wanted to ask you about a bit is about this direction towards a quantum internet. You're probably aware that we have a BRICS collaboration between China to develop a satellite-based quantum network by the year 2021 or 2022. My question to you is, what is this importance of this, every country developing their own kind of quantum network that is based on satellite and fiber communication, as well as what are some of the challenges that we can face when going about developing a quantum network that will hopefully future lead to a quantum internet? So
yeah, well,
some
yes, thank you, Sira. Yeah, good to hear from you. There are challenges, of course. So the challenges can be roughly divided into technological challenges and I would say legal/political challenges. The technologies is kind of obvious. So we want to rely on a hybrid technology which combines satellite, long-distance satellite communication with optical fibers. Both of them have pros and cons, and so the future quantum internet would have to be based both on on-the-ground optical fiber kind of system and working together with satellites. So yeah, the technological challenges are related to better sources of entangled photons, better detectors in a given frequency range, better, better systems for tracking satellites, and so on and so forth. So those things are in the domain of technology, but there are some other issues as well which are equally important. For example, there's no point to have quantum internet if you don't make a standard for secure quantum communication. So if two nations that are not necessarily friendly, but they want to talk and exchange secure messages, then they have to agree on standard. So the standardization is a very important issue. When it comes to satellite, there are some issues about, you'll be surprised about entangled photons crossing borders. So you have on the ground having optical fiber going from one legal entity to another legal entity, or from one country to another country. That can cause lots of problems. But the satellite somehow can bypass this in some way. So I think that there is a need both to push technology, that's probably the most important for scientists, but of course there's also a need for work on the ground to create agreement about what kind of standards are we going to have, what kind of legal solutions are we going to have for this kind of communication. So that shouldn't be too difficult, right? So that it happened for classical communication. We can repeat the whole thing for quantum, but the quantum is still new. It's still not clear how the government agencies, for example, still have some issues with understanding this. Just to give you one example, some time ago here in Singapore, people from the local casino authorities came to ask whether quantum random number generators might be more fair and there's no way to compromise them, or whether quantum technologies can have a power to make some of those games of choice or more predictable, may give advantage to someone. So there's a clear concern on the agency side. I thought it was very nice that someone read about it and thought about it and see some regulation and legislation related to quantum technologies. And here one has to strike a sort of a reasonable compromise. Not regulation should not make more difficult to develop technologies, but should somehow make it easier for us to collaborate and establish working prototypes across different boundaries and different borders. It's probably, I don't know whether this was exactly what you were asking for, but
yeah, I just wanted you to touch a bit more, because as an expert in the field, and we're starting now this development of a quantum satellite project in South Africa. So it will be the first intercontinental link for us. And we will be working with the Chinese group that launched the MISCUS satellite. And of course, we're going to be facing both these challenges that you mentioned. So thank you.
Thanks. Well, I'm sure, you know, with you have a number of experienced people, and I trust Francesco will be able to make sure that you collaborate with the Chinese colleagues without any glitches, and then the standards are there, so that's, I wouldn't worry too much about Yazira, about the political things.
Okay.
I would be much more concerned about scientific side.
Okay, let me read a couple of questions which people wrote. So one is a kind of more on the kind of how to put it, on the fear problem of the quantum computing. So if the development of the quantum computing yield the progression of reliable qubits in quantum systems, what crypto systems are more likely to be rendered unsafe first? Public-private key page generation using the elliptic curves, or hash functions, assuming the same size of the key space, for example, of 256 bits?
I think that well, we know that the elliptic curves are going to be vulnerable to quantum attacks, like together with RSA. And so that means, for example, that digital signatures, which are based on elliptic curves, are not secure as far as quantum attacks are concerned, which, for example, is a big issue for cryptocurrencies. Whether we can fix it with this quantum or post-quantum crypto, as some call it, or quantum-resistant cryptography, I think we can, even though it's not going to be that easy. I'm not sure whether the question was like, what, it's difficult to speculate what are the best alternatives to public key crypto systems. It could be perhaps, you know, I would say perhaps lattice-based crypto systems might be those that that offer some extra security and resistance to quantum attacks, but it will be very difficult to prove it. So I think it's very difficult to design a system that you can say it's a classical system, that you can say it's provably secure against quantum attacks. We may have a situation, as we have it now in classical crypto, that we have RSA that is based on the difficulty of factoring. Nobody knows really whether it's inherent difficulty. It could well be that a classical factoring algorithm that is efficient will be found. We simply don't know. So in this sense, public key crypto systems like RSA are not proven to be secure. And we know that they are vulnerable to quantum attacks. So it may be the same situation, that we come up with a system that is which is not known to be really, or we cannot prove that it's really secure because we cannot prove that quantum computers will not be able to find certain vectors on certain lattices in an efficient way. But it may be the case that everyone will try and nobody will be able to do it. So the status of the security of this post-quantum thing may be very similar to the current status of RSA.
Okay, great. And there is a couple of questions from Ismail. And let me start on the second one because I think it's more interesting, but I'm obviously biased. How much do you think of device independence would survive after successful theory of quantum gravity, meaning the Hawking radiation plus cloning is currently used to produce new paradoxes like black hole fireballs and so on?
I think it will survive because it doesn't even rely on, you see, the violation of the Bell inequality as such is not a statement, that comes from quantum physics. It's a statement about correlations. And it says, okay, here is a statement about correlations. There's an inequality. When we derive Bell inequality, we never use any quantum physics. We just use a very simple probability theory. And then we just go on and say that there is a quantum theory, and quantum theory makes predictions that there are quantum correlations that violate those Bell inequality. Now, if we then have a new theory that goes beyond quantum, or modification to quantum, if those correlations, no matter how you call them gravity-induced something or the other, or call them post-quantum, but in a different meaning of post-quantum correlations. So that kind of correlations, as long as they violate the Bell inequality, one would be able to extract secure information from those correlations, as long as, of course, as long as there are well-defined outcomes from measurements and so on and so forth. So I wouldn't, so that's another beauty about device-independent crypto. It doesn't even refer to quantum physics that much. Of course, at the moment, if you assume that it's security, that people constructed also security proofs with respect to non-signaling correlations. So those are the correlations on my diagram that go beyond quantum. We don't see them, we don't observe them, we don't know whether nature is like this. But it is known that if we are to see them, then we can also put an upper bound on this mean entropy and then start calculating secret key rate. So I would be positive. I think that the device independent is very powerful.
Okay, thank you. And let me jump to the questions. I mean, the speakers are reading up these questions because they're not sure that they can manage in time. So let me read it because I hope that will be faster. So the question from Thomas is, the bottleneck of QKD seems to be in the missing bandwidth. Do you think QKD with optical modes instead of polarization will help to improve the bandwidth of QKD channel, or rather continuous variables or combination of both?
I actually, probably combination of both. It depends very much on the context. And I think that essentially, I believe that the new detectors will just lead to a better data rate. And so I'm not so much concerned. As long as it is comparable with public key crypto systems, which I think is getting there, it's not probably going to be as fast as the conventional secret key method used by in cryptography, but I wouldn't consider this as a big issue.
Okay. And the question from the ESAT is, my question relates to the channel authentication. While it is necessary to have an authenticated classical channel. What about quantum channel? Are there quantum tests that can confirm that Alice and Bob's quantum systems are not compromised?
Yeah, it is a very good question. Of course, yes. So here, for all practical purposes, we are talking about key expand. We assume that there is some secret that we use for authentication. Otherwise, I was describing a little bit more academic scenario where Alice and Bob have access to public channel, and having access to public channel means that it's like a broadcasting, where public broadcasting or announcement in a newspaper, where everyone can listen to this public channel, but nobody can change information in the public channel, in this broadcasting channel. So that would, to some extent, eliminate this danger where Alice pretends to be, an eavesdropper pretends to be Alice towards Bob and pretends to be Bob to Alice. It's called a man-in-the-middle attack. So then if Alice and Bob start listening to a broadcasting channel and hear conflicting messages, then they know that something not quite right. But that's not how it is done in practice. In practice, you really want to have authentication. And Alice and Bob, usually it's assumed that if they have a key distribution session, that they leave part of the key for the subsequent authentication in their communication. So it is a good point. This is sort of needed.
Okay, thank you very much, Artur. I'm looking at the time, and I think we are slowly getting out of the error margin. No, thank you very much, Artur, for a fantastic talk. And you saw from the large number of questions that there's lots of interest here for your work and for what is going on in the field of quantum cryptography worldwide. So again, thank you so much. I know that it's late in the evening for you in Singapore, so we wish you a good night, and again, thank you so much for your talk this afternoon. Thank you, Artur.
It was a pleasure. Thank you very much for inviting me.
No, thank you very much, Ilya, and thank you to all the participants for being so faithful to our NITheP Colloquium. Thank you very much, and have a good evening as well.